Hello everyone, today we'll talk about the solution to the problem fill in bookcase shelves. Feel free to pause and read the statement if you're unfamiliar, and we'll talk about the solution. We have this list of books with thickness and heights, and one way of looking at the decisions that we can make when we run the algorithm is that we can insert some number of separators between some positions of that list of books. And that separator means that, okay, everything from the previous separator, or the beginning of the array, goes as a single shelf. And of course, then the total thickness of those books cannot exceed shelf width. And then we create a new shelf. And you want to optimally insert those separators. And if it wasn't clear before, then by looking at it like this, by having this binary decision of either we separate here or we don't separate here, that this problem can be solved using dynamic programming. And probably the most natural way, at least for me, of looking at a formulation for dynamic programming would be that for every book, for every position, we choose that book to be the last book on its shelf, and then maybe we go back in time and try to add some previous books to that shelf and see if that improves our result. Because we know of all the possibilities, we know that this one is always possible. So our DP will hold the answer for the first I books, so the minimum possible height of those previous books, and we cannot add anything to those shelves that we used before. And now when we have a new book, we know that we can take that book, create a shelf of appropriate height, and that is a possible result. So we take the arrangement of the previous books as they were, create a new shelf, add our book to that shelf, and that's it. However, of course, we might also want to add some more books to that shelf, but those will be previous books. So we look at previous books, while maintaining both the current height, which at the beginning is just the height of the current book, and over time will be the maximum height of the book that we've used, and also the remaining width, the remaining thickness that we have on our shelf that we're building. And now for every previous book, if it fits on our shelf, then we either take it or we don't take it. And of course, we might take it. And in that case, we want to look at the result for all the previous books, take that result, and also add the current height of the shelf, while the current height is, of course, the biggest height that we've seen on our current shelf. So in particular, it might be the height of the current book that we're looking at. And of course, since we're maintaining the width and height of the shelf that we're building, then we might not be changing this DP too much, but we are always looking at the shelf that includes the ith book, and a single previous book, 2 previous books, 3 previous books, because we have to maintain that on every shelf there is a contiguous sequence of books. And at the end, of course, since we know for sure that the last shelf ends at the last book, we just return the last position on our DP. This is a very straightforward n-squared DP. And, of course, you might think, especially considering how regular those DP values are and how simple the process is that we perform to do the changes to the DP, if it's possible to do it in faster than quadratic time. And of course it is possible to do it faster, and it's possible to do it in n log n. I also think that it's possible to do it in linear time with some monotonic stacks, but this is an exercise to the watcher.